This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right, good morning, everyone. Sorry, for the last couple of weeks I've been very sick, so my enthusiasm for anything is pretty low, so I apologize for that. I hope I recover soon. I have a question for you. Have you seen like a poster around the campus in Chinese, and the only English words were control systems? I'm wondering what that is about. I can't read Chinese, so can someone help me? Has anyone seen what it's about? You can speak up. I mean, I'm just curious. Has anyone seen it? No? All right. Well, it's it's interesting. So there's control systems, and then Chinese, then PID Chinese, root locus Chinese. So I would just like to know what it's about. Probably someone's offering lectures in parallel or something. Anyway, I'm just curious. So, all right. So today's lecture is actually a turning point. It seems like just another name, root locus, but it's a turning point in your study of control systems because it's the first lecture in which I will talk about design. So in the last couple of lectures, we were learning how to translate specifications for design into some locations of closed loop poles, and also for steady state errors. We saw, okay, the gain at 0 has to satisfy certain conditions. But in today's lecture, we will for the first time learn how to design controllers that satisfy some specifications. Right? So it's an introductory lecture. Most of the details of how to sketch this root locus will be presented in tomorrow's lecture. So today is just an introduction lecture. But in terms of concepts, this is very important. So because we are going from analysis, which we are used to in civil systems, to design. And this subject is all about design. So you will see that root locus is an important design tool. So this object called root locus is an important design tool. It's not universal in the sense that sometimes you may not be able to design the controller you want using this tool, but in terms of conceptual understanding, it's very important because it's the first design, it's the simplest design technique that you will learn in this subject. So this is why I believe this lecture is very important, to grasp the concept of design. Okay? So here's the outline. So first I'll motivate things a bit. Then I'll talk a bit about problem formulation, a bit of history, and then we will present two fundamental properties of the root locus, which are phase and gain condition. Next lecture, tomorrow, you will see that every property of root locus, or every rule for drawing, sketching root locus, will follow from these two properties, phase and gain margin conditions. I'll also give you just like one slide on how to use MATLAB. MATLAB does this very quickly. So there is just R locus command, and if you define your system via its output as a function, it just does it for you in a matter of seconds. And then what we'll do next is talk about main features of root locus. Now, why do we do this? you will see that sketching root locus by hand can be done very quickly if you can figure out some of its main features and then you connect everything. Now, in this lecture we will just introduce these main features, and tomorrow we will show how to sketch these main features for given examples, okay? And then we will wrap up with conclusions. So, what we saw in previous lectures, two previous lectures, was first that choice of controller, or in other words, zero gain of the controller would affect steady state errors. And we also saw that, overshoot, rise time, settling time requirements can be translated to the desired locations of the closed loop poles, right? So in other words, in the last two lectures, we learned how to translate some of the requirements of your closed loop system into some sort of location of closed loop poles or open loop gain at zero for steady state errors. So today we want to now start playing with the controller and sketch how poles of the closed loop system move as a function of this gain in the controller. So that's pretty much what root loops is all about. So yesterday we saw that if I give you conditions on settling time, rise time, and overshoot, we can come up with a region in complex plane that looks like this. By the way, what these sort of lines, these sloped lines correspond to, do you remember? Zeta, that's damping, but in terms of features of step response, which one is captured by these guys? Overshoot. How about this bit of circle? What does this relate to? Rise time, and this vertical line is settling time. So if I give you conditions on all three, you in general get something like this. And then the question is, can you design a controller so that you move the poles of the closed loop system to be in this white region, right? Desired region of the complex plane. Why do we do this? Because then we would satisfy our desired specifications. Okay? Now we want to learn how to do that in the simplest possible case. Here's an example. So suppose we have a transfer function given by G0. So B0 and A0 are polynomials, right? So this is a rational function. G0 and A0 and B0 are polynomials. So I would assume that controller is in the feedback loop, and I will assume that controller has the simplest possible structure. It's just a gain. It's a static gain. The controller doesn't have its own transfer function. It just has some gain, and gain it will be assumed positive, just for the sake of argument. I will assume gain positive, and I want to now plot how poles of the closed loop change as a function of k. As I vary k from 0 to infinity, I want to see how closed loop poles change in complex plane. So for any value of k, locations of the closed loop poles will be determined by just G0 and k, right? And I want to plot now this as a function of k, these poles as a function of k. So that actually is root locus. So what is the desired question? Well, can we select k so that the poles of the closed loop are in the desired region, like in this white region? Right? So first I give you specifications, you come up with the desired region, right? And then you're saying, well, can I now find k here so that the poles are moved to the desired region? That's design. That's exactly design, because typically in design, you are given a set of specifications, and then you have some parameters to play with. And you need to design these parameters so that you satisfy these specifications. That's exactly what design is. Are there any questions? All right. So note that if we look at things in more detail, the transfer function of the closed loop is given by this formula. We saw this in algebra of block diagrams. Note that k is the controller transfer function and G0 is the plant transfer function. So we've seen this in algebra of block diagrams. Now, how do we find poles of this closed loop transfer function g? Well, we need to look at roots of 1 plus k b0 over a0. So we need to equate this to 0 and solve it in S. So for each fixed k, we will have a different set of solutions. But know that this is equivalent to looking at something like this. I just multiply everything by a0, and then I can be looking at a0s plus k b0s. And so solutions of this equation or that equation will be the same. And these solutions would be basically poles of the closed loop transfer function. So now the question of design is, well, can I pick k, well, so that I satisfy all specifications? But before we can answer that, the question is, as I move k, as I change k, where are the locations of zeros of these polynomials? So that's exactly what root locus is. Root locus is telling you where the locations of these solutions of this equation are in complex plane as k varies from 0 to infinity. Okay. Let's look at a simple example. So what I'm now doing is I'm specifying Planck transfer function to be something very specific. So open loop transfer function has a pole at 0 and has a pole at minus 1.5. And I want to now plot how closed loop poles change as a function of k. Well, if I look at the closed loop characteristic equation or closed loop poles, well, I need to solve something like this. How did I get this equation? Well, I got it by looking at 1 plus k times g0, and I equated that to 0. That's exactly what's given here. So in this case, g0 is 1 over s times s plus 1.5. So that's what g0 is, right? And then I plug it into this equation, and this is what I get. This is what I get. All right. So because it's a second order polynomial, I can explicitly write solutions of this second order polynomial, like zeros, right? So two solutions, two poles, two closed loop poles are given by this equation. So let's just stop and sort of analyze a little bit what happens to the closed loop poles. So these guys here are solutions of this equation, and solutions of this equation are giving you closed loop poles for this system. Okay? So when k is 0, what do we get? Well, when k is 0, we have two real poles. One pole, so when k is 0, I have square root of 1.5 squared. So this is really minus 1.5, and then I have plus minus 1.5 divided by 2. When I use plus, this is 0. So one of the closed loop poles is 0 when k is 0, and another closed loop pole is at minus 1.5. Because I have minus 1.5 divided by 2. That's why minus 1.5. How about when k is equal to 1.5 squared divided by 4? I still have two real solutions, but they are both located at minus 1.5 divided by 2, because all the thing in square root is 0. The square root is 0. So in that case, for that value of k, I get two real poles, both at minus 0.75. How about when k tends to infinity? When k tends to infinity, then this part, which is positive, is negligible. So we will end up only with the part that depends on k, almost, right? So, and it's negative because we assume that k is positive. So we will have these real part of these poles would not change, it's k independent, but imaginary parts would blow into infinity. They would be larger and larger as k is larger and larger. So plotting all this in one plot in complex plane is root locus. So root locus for this particular example is given here. So these green lines and blue lines are exactly root locus for this particular example. So let's just go back to what we were talking about before. When k is 0, then we said the closed loop poles would be at 0 and minus 1.5. Let's look at the root locus. Well, when k is 0, that would correspond to this. There's a little cross here at 0, and there is a little cross here at minus 1.5. So that exactly corresponds to the solutions for k equals 0. When k is equal to 1.5 squared divided by 4, then this square root is 0. Then we said we have minus 0.75. Look at this. This is that point, right, where these two branches meet. And then as k is increased, then we said the real part doesn't change, but imaginary part goes up to infinity. We have two complex conjugate poles of the closed loop. So what you see here is called root locus for this example. Blue and green parts of the root locus are called branches of root locus. Why? Because there is, for each of these branches, so each branch corresponds to one pole of the closed loop system. So for each fixed value of k, gain of the controller, there would correspond some point on this branch, which is one of the poles, and some point on that branch, which is the other pole. Okay? So typically you will have, a number of branches. This is just a simple example where you have two branches. You can have much more complicated situation than this. So we will learn how to sketch root locus. You can say, oh, well, I have MATLAB, MATLAB can do that for me. MATLAB sometimes produces outcomes that will be very hard to interpret for you if you don't know the rules for sketching the root locus. And also in the exam, you will be asked to sketch root loci for some examples, right? So you won't have a computer, and you will see it's very insightful. This is a tool, but it's a tool that gives you a lot of insight into design. Okay? So that's why it's a simple tool, not universal, wouldn't always solve your problem, but you can get a lot of insights from using this tool. So that's why it's very important. Okay, so this is now, first time we've seen a root locus. We will talk more about root locus. This is an introductory lecture. Tomorrow we will go through an example and we'll show how to calculate various features of the root locus and then put them together to sketch a root locus very quickly. Right? So you will learn that tomorrow. Now, where does design come in? So I plotted this exactly in this way so that you can see that design may be tricky. So why design may be tricky? If you were asked to place the closed loop poles in the white region, so you translated your conditions on overshoot, rise time, and settling time into desired locations of the closed loop poles, and if you were exactly dealing with this example, then the root locus, I just copied the root locus. This red plot is exactly what's plotted here, right? And note now that this is one branch, so basically for any fixed k, there will be one pole on this branch. So for as long as you're on this branch, k is low, then you will be in the forbidden region, one of the poles in the forbidden region. As you keep increasing k, the two poles would meet at this point, for k equal 1.5 squared divided by 4, and then as you keep increasing k, you will start having complex conjugate poles. Now, it's interesting that only in this region, for k's that places poles in this region, everything is symmetric, right? Everything is symmetric. So gains that correspond to this part of the branch will be exactly the same gains that correspond to this part of the branch. Everything is symmetric. So know that there will be some region of k's for which you do satisfy your requirements, but then as you keep increasing k, you again do not satisfy requirements. So tuning the k is tricky. And this really exemplifies, although it's the simplest example you can think of, this does exemplify the art of design. Right? Because you need to come up now with exactly the values of k that will place you in this white region, right? And depending on the example, the white region will change, specifications change, and also depending on the example, root locus will change. But you need to be able to now do design in this way so that you place all closed loop poles in the desired region of the complex code. So while this is not a universal technique, right? It would not solve your problem always. It's a very insightful and very easy to explain what design is all about. What you can play with is K. Root locus allows you to plot how K affects closed loop poles, and then you need to do something like this. You need to find the values of K so that root locus is in the desired region of the complex code. That's design. Any questions? Okay. Yep. Good? Okay. All right. Now, root locus is much more general than just that situation I presented earlier. Root locus may be plotted for systems where controller is not just a proportional controller. The first example I presented was just the controller was a proportional controller. So the controller here was just K. Here I'm using controller which is not just proportional controller, but after some algebra of block diagrams, I can rewrite the characteristic polynomial as a function of K, where now this D and M do not correspond to G0 directly. They are not numerator and denominator of G0, but there are some other polynomials that I can obtain just through algebra of block diagrams. So you can rewrite this characteristic equation, which depends on K, still in the same manner as what we dealt with before. Know that before we dealt with this, where B0 and G0, B0 and A0 came from G0 directly, but in general, they may not be exactly the numerator-denominator of the Planck transfer function. They can be some other polynomials. Which polynomials? That depends on how controller is parameterized with gain K, right? So in this case, you just get these polynomials. So basically, controller structure doesn't have to be just proportional. It can be something else. But you will have to rewrite everything in this manner, and then you will be applying root locus to something like this. So root locus will be applied to equations that look like this. But you might have to have some steps to use algebra block diagrams to arrive at this form for any particular example. That's one observation. Another observation is that gain K may not even be in the controller at all. What you might do is you might say, all right, I don't know my Planck model. I'm not sure what my Planck model is. And then I'm saying I'm using controller. I here say, okay, let me just try to use controller, which is just simplest controller. There is feedback loop. What you can do is you can again find the characteristic polynomial for the closed loop system by algebra block diagrams, rewrite it again in the way that we described before. We get the same mathematical description of where the locations of closed loop poles are. And you can analyze how closed loop poles are affected by this Planck parameter K. So this can be used as a robustness analysis tool. So I have a given fixed controller, and then I'm looking at how a Planck parameter affects stability of my system or performance of my system. Okay? So you can use root locus in this situation. So one disadvantage of root locus is that it deals with one parameter only. There are generalizations of root locus for several parameters, but you can imagine that it's not as easy to plot, and it's not as easy to interpret, especially if you have 3 or 4 parameters. Forget about plotting things. 4 parameters you can't plot, graphically. Root locus is simple, but very powerful. And you will see that lots of intuition on design can be gained by understanding root locus in depth. So actually understanding this material in depth would allow you to understand a lot of general statements that I will be making later on design, how to design control systems. We will be gaining a lot of intuition from this simple tool. All right. Interestingly, this was proposed by a person, Bill Evans, who is his name, who didn't even have a PhD. So he worked in different research labs. You can recognize maybe some of the names of these companies, General Electric, for instance, Rockwell, Ford. He received Richard Bellman Control Heritage Award. It's the highest award you can get in control engineering. So, and he didn't even have a PhD. Why is this? Well, because it's so useful. Root locus is so useful. It's simple, it's not general, but it's so useful. And that's why he was recognized by this very, very prestigious award. All right, so that's the phase behind this tool. All right, so what we want to do now in the second part of the class, we want to formulate the problem in more detail. We want to identify main features of root locus, and then I will introduce, through an example, features that we will learn how to plot tomorrow. So tomorrow we will be looking at how to plot things. Today we want to learn the names of different things, right? So that's because this is an introductory lecture. So what we will be starting from is an equation that looks like this: 1 plus k times f of s, where f of s is just m divided by d. M and d are polynomial, and they can be rewritten in this form. So I will assume that the top and bottom can be just rewritten as a product of s minus zeros and then s minus poles at the bottom. So beta k and alpha k are respectively zeros and poles of this transfer function. By the way, this transfer function may not correspond to either transfer function of the plant or controller. It's just an artificial construct that will allow us to plot closed-loop system poles for the system at hand. But they may not be in any way related, or they're not just a plant transfer function or control transfer function. You have to obtain them for every example separately, right? So what we want to do, we want to now plot how zeros of this, or solutions of this equation, change as k varies from 0 to infinity. So you may ask, well, why 0 to infinity? Well, we already have a negative feedback. There's some good reasons for it. It's not needed. You can plot everything for negative k, but then that's called a negative. So we will assume in everything we do that we're just plotting positive root locus where k is positive. In other books, in Ogata and other books, you would find, how to plot negative root locus. Lots of things I will present can be used to plot also negative root locus, but you can figure it out yourself as we go. It's not hard to figure out. But we are assuming that k is positive, all right? And we call that positive root locus. So let's just look at some very simple observations. So I'm saying first, if a point is S0 or in complex plane, if I pick a point in complex plane, which I call S0, if that point is on the root locus, then that point, that S0 needs to satisfy this equation. If I plug in S0 into the transfer function, right, it has to solve the equation. If it doesn't solve the equation, then S0 is not on the root locus. So by the way, if I go back to my example, so if I pick a point here and I plug this point into my equation, it won't be 0. But if I pick this point and plug it into the equation will be identically equal to 0. So that's basically, well, that's how the root locus is defined, right? And so that's the first one, but note that I can rewrite this equation in this way, right? So since I can rewrite it in this way, I can see that k times f of S0 is equal to -1. Well, what does that mean? Well, magnitude condition has to be satisfied for all points on the root locus. If I take the magnitude of the left-hand side and right-hand side, I get just 1, right? Because magnitude of the right-hand side is 1, and that is equal to the magnitude of the left-hand side. And moreover, the phase of k times f of S0 should satisfy this equation. Why? Why is this? Why am I saying the phase of k times f S0 should be equal to pi plus minus pi? Because it's equal to minus 1. And phase of minus 1 is exactly what's written here. Right? Phase on the left-hand side, right-hand side should be the same. Note, I assume that k is positive. What does that mean? Well, phase of k is 0. So I can just forget about k. Phase of f S0 should be satisfying this phase condition. So this is actually, these two equations are fundamental to sketching root locus and understanding the properties of root locus. And we will use them over and over again tomorrow in the lecture when we start plotting root locus. Are there any questions here? All right. So what I want to do now, I want to graphically represent what a phase condition looks like. How can you graphically check it quickly, right? So what you can do is you can say, well, because k is positive, then I would say, so going from here, k is positive, then phase of k wouldn't affect things, right? So I can just say that phase of f is equal to this, right? So that's what's rewritten here. But phase of f can be rewritten as phases of S0 minus beta k, sum of all phases, minus sum of all phases S minus alpha k. Beta k's are zeros and alpha k's are poles. So I remind you that the alpha k and beta k come from here. So this is a simple formula on how to calculate the phase. Now, what does this mean? This sum of these guys minus sum of that guy. How can we graphically represent this? Here is an example. Look, what's given here is that black point is S0. So that's a test point. I'm saying let me pick an arbitrary point in complex plane. But I know that poles and zeros of the transfer function f, right, are known to me. I know f. So I can plot what poles of f are, which are alpha k, and I can plot what zeros of f are, which are beta k. I represent poles by crosses and zeros by circles. So I plotted poles in this example here and 1 0 here. So what are these phases? Well, I connect all the poles and zeros with lines to the S0 point, black point, and then I just read off the angles, the corresponding angles. So this angle here, so always looking at positive real axis and the line that connects me to the S0, that's basically the phase of S0 minus beta 1. So that's basically, I'm constructing these guys. That's how I can actually graphically construct them, just connect everything and measure the angles, and off we go. And similarly, we have for each of the poles phase contributions from each pole. Now, what is the test phase condition for root locus? If you add these guys, so in this example, we have 1, 0, and 3 poles. If this thing here is exactly equal to some maybe pi, plus minus 3 pi, etc. If that's the case, then point S0 lies on the root locus. If that condition is not satisfied, then the point S0 does not lie on the root locus. That's how you can quickly check phase condition for any point that you pick in the complex plane. You know, you can check this graphically. So this is all good, and we are just sort of talking about gain and phase conditions. We will use them later for sketching things. Note also that since the root locus is parameterized with gain k, if we want to calculate value of k that corresponds to a specific point of the root locus, suppose I pick S0 on the root locus, then the k that corresponds to that point can be calculated this way. Right. So what does this mean? if I go back to my root locus, let's say here, I pick this point and I say, what is the value of k that corresponds to this point? Or let's say this point, which is at the intersection of the desired region and root locus. Well, this is my S0. I plug that S0 into f of S0, and k is 1 over norm of f S0. So k gain corresponds to that point. All right. So this gain condition is also very useful in a range of design scenarios. All right. So I will now just show you, like in a slide or two, how to sketch root locus using MATLAB. It's very useful. Okay, the command is RLocus, right? So you define your transfer function. So transfer function is f. The transfer function in 1 plus kf equals 0. You define f, and then you just use RLocus f, right? Transfer function. But it's also useful to know this function sgrid, which gives you also grid of constant damping factors and constant natural frequencies, because this is very useful for design. So let me just show you in an example. So look, root locus, so what is given there? 1 is basically what's in the numerator of the transfer function, and then this 1, 3, 2, 0, these are the coefficients in the polynomial in the denominator of the transfer function. And I just use rule RLocus. That RLocus command would give me this green, blue, and red lines. There are 3 branches because there is a third order polynomial in the denominator there in the transfer function. But if you put this sgrid command, then it will provide these dashed lines. And these dashed lines are really useful because they give you lines in complex plane where you have constant natural frequency or constant damping. So you can then say, well, at this point, I know exactly what natural frequency is corresponding to this point of the root locus, and what is the damping, right? So it's just a useful design tool. So it's very easy to plot things using MATLAB, and you will see we will spend some time learning how to sketch root locus by hand. It's because intuition you gain from it is really invaluable. Intuition you gain from root locus is invaluable. So any control engineer should really master this intuition. Okay. All right, so I've shown you how to plot things using MATLAB. Now what I want to do in the rest of the lecture, I want to consider one example, and I want to name certain features of root locus, because tomorrow we will be plotting each of those. We will use gain and phase conditions to plot each of these features of the root locus in tomorrow's lecture. By hand. You don't need, you might need a ruler, compass or something, just simple drawing tools, but you will be able to draw this very quickly, sketch very quickly. So what are the main features of root locus? Well, first, the number of branches. How many branches it has. Open loop poles and open loop zeros are crucial for sketching the root locus. So they are the poles of transfer function f and zeros of transfer function f. What is the transfer function f? It's this guy, right? So I'm looking at 1 plus kf, right? That's the equals 0, and I'm talking about f transfer function. Parts of real line that belong to root locus, you will see you can very quickly determine parts of real line that belong to root locus. Asymptotes, as we increase k, some branches might go to infinity, and they typically approach these asymptotes. You can quickly plot asymptotes. Breakaway point, in other words, where branches intersect. Intersections with imaginary axis and angles of departure or arrival. So each of these are a feature of root locus, which are such that if you know all of them, if I give you all these features, you will be able to sketch root locus just using this partial information. You don't need to plot point by point. You can quickly sketch root locus using these features. And this is due to Bill Evans. He actually came up with all these sort of cool, quick ways of sketching the root locus. So what we will do in today's lecture, we will, through an example, talk about each of these just to familiarize ourselves, And tomorrow we will learn how to plot them, how to calculate them for any given example. So here is the example that we already considered. So I'm just using the same example that I plotted in MATLAB. So what you can see here is basically all these crosses are open loop poles. I remind you that in the example we have, so f of s in this example is given by 1 over s times s plus 1 times s plus 2. So the open loop poles of f are at 0, at -1, and -2. So note then that these guys are included in the root locus sketch. These open loop poles are always very important feature of the root locus. They are always there. In this example, we do not have any zeros, but zeros will be denoted by circles if we had any. Okay? So, open loop poles are points where branches of root locus start from. In other words, for small k, how do we see this? Well, if I cross-multiplied everything, so if I cross-multiplied everything by d, right, then it will be d plus k times n that I'm solving. So when k is 0, I just am solving for d. So they are the open loop poles of the f, right? So that's why when k is small, we know that branches of root locus will hang around the open loop poles. Now, what are the parts of real line that belong to the root locus? In this example, these are the red lines that I presented there. So it turns out that it is very easy to discover which parts of real line belong to the root locus. We will use phase condition to show this. We won't show how to do that today, but I'm just identifying, well, this is a feature of root locus that we will be able to plot quickly. So know that this part of real line in complex plane belongs to this root locus, and similarly this part of real line belongs to the root locus. Asymptotes. In this case, note, if I go back to the root locus, know that this green branch somehow tends to a line. If you look more closely, it looks like a line. That's an asymptote. Blue branch also tends to a line. And this red part is also like a line. So each of these we will call asymptotes. As k goes to infinity, branches of root locus, a number of branches of root locus would tend to these asymptotes. So if you sketch these asymptotes, you will learn a lot about the shape of the root locus just from that. So what are the asymptotes? Well, in this case, they are plotted here. So what we will do is we will show how to determine the point where all asymptotes intersect and angles of each of the asymptotes. So we will learn how to plot that tomorrow. We will give formulas. But at this point, just know that some root loci do have these asymptotes. So, as I said, these asymptotes are determined by a point where they intersect real axis and angle with the positive real axis. We will learn how to do that in general, how to quickly plot these asymptotes. Another sort of important part of root locus is this breakaway point. Note, for as long as d is small, we will have 3 real poles, because all poles of the closed loop transfer function will be on the real axis. But as we keep increasing k, 2 real poles will meet, and they will meet exactly at this point, this red point. Now, this is the point where the roots will be basically exhibiting multiplicity. So you have 2 real roots which are exactly the same. Now, we will learn how to find such a point. Why is this point important? As you keep increasing the gain, this is where the branches would branch out from the real axis, and then you will have complex conjugate poles corresponding to these branches. So this point, we will learn how to find it. So that's called breakaway point. this corresponds to repeated poles. Another important feature of root locus are intersections with imaginary axis. So know that in this example, two branches of root locus intersect the imaginary axis, and as we keep increasing the gain, these branches, blue and green, would end up in the right half plane. Now what does that mean? It means that for sufficiently high gain, the controller would destabilize the system, because we will have two poles in the right half plane. Okay? So determining exactly where these intersections with the imaginary axis are is very important. And also determining the value of the gain k at which this happens is also very important. Okay? So this is another feature of root locus, which we will learn how to find these intersections of branches of root locus with the imaginary axis. And finally, here I present another example because I need to introduce a new feature which the original example doesn't exhibit. So here is an ugly transfer function there, right? And I plotted root locus that looks like this. So sometimes when you have complex conjugate poles, open loop poles like this, you don't know whether the root locus would go this way or that way or that way. So in other words, departure angle at which root locus departs from the pole is very important in sketching the root locus. But, so because this departure angle is exactly the tangent on the root locus at this point. So if you have this tangent, it helps you sketch things. Similarly, you can calculate angles of arrival at zeros using the same tools. Tomorrow you will see you use the same formulas, phase condition, to calculate these angles of departure and arrival of root locus. What can you tell me about this root locus? What's so interesting about it? Look, this system cannot be stabilized by any value of control gain. Why? Because this red branch and this green branch are entirely in the right half plane. So no matter how you choose your gain, there will be two complex conjugate poles that are in the right half plane. You cannot stabilize this system with that parameter. That doesn't mean that the system cannot be stabilized in general. If I change the controller, if I change the parameterization of the controller on the gain k, I might be able to stabilize, but not with this parameterization, with this parameter that I'm using. All right. So, so what is important to take from this lecture is, you know, you will, in any root locus, positive root locus, we need to satisfy these gain and phase conditions. Gain and phase conditions will be used, plus other things, will be used to sketch root locus very quickly. Now, this is not just me forcing you to do something that MATLAB can do anyway. Any intuition you gain from root locus would be invaluable for this subject, invaluable for design. So lots of things, lots of general statements can be made just based on root locus. You will see when we start talking about tuning PID controllers, we will use root locus to gain intuition about that. So MATLAB can be used to do things very quickly, to plot very quickly. And what we will do in the next lecture, we will present formulas so that you can find exactly each of the features of a given root locus. If I give you an example, you can find number of asymptotes and plot asymptotes. You can find part of real axis that belong to root locus. You can find open loop zeros and poles, departure angles. You know, all of those features that I gave you, we will learn how to plot. And once you have all of them, then it would be just a matter of, you know, it's like forensics, you know, it's crossword puzzle. You just connect things. If you solved a few examples, you would know exactly how to connect things. So sketching root locus is very easy once you know all these features of the root locus. So in this lecture, we introduce these features. Tomorrow, we will learn how to plot them. So, just conclusion. So what is a root locus? It's a plot that shows you how closed loop poles change as some parameter is varied in your system, usually control parameter, but it can be plotted as well. MATLAB can quickly plot this. We showed, you know, the main conditions, phase and gain conditions. And we listed features. Tomorrow we will learn how to determine features for any given example, right? And then how to plot the sketch groups. All right, questions? Thanks. So if someone can send me, an email about what that poster about control systems is, I'm very curious. All right, thank you. Damping. I wouldn't call it damping frequency, I'd say just damping.
Just damping.
Yeah, so natural frequency are these semicircles, and damping factor are these lines. Yeah.
Damping is line, natural is the circle.
Yeah.
But I cannot see, for example, what is the natural for this line here?
Sorry?
What is the natural for this line here?
If you plot this and then you put, MATLAB can give you exactly what is the natural frequency for this guy, so you can read it off from here.
Okay.
So this is the basically natural frequency.
Okay.
So that point here.
Natural and damping.
Yeah.
Thank you.
I didn't notice this section. You said what condition you said, which it's basically
Phase condition.
and
So phase condition is given here in general, and this is just an example.
so if you add them all together,
Yes. So how do you get each of these phases? You connect S0 with each pole, H0 and pole, you get these lines, and look at the angles between real positive line and this line, and that gives you these individual phases. Can you take it outside, please? Because there's another lecture here. Because phase of this should be equal to that.